Good afternoon, everyone. This is Andres. Thank you very much for joining this presentation. The work presented is done by the people listed here who belong to these institutes, and the title refers to the work done to treat the problem of data classification using a definite machine learning algorithm with boosting techniques, which at the end we would like to apply to high energy physics experiments. Okay, in real life or nature, we find that the data is described by many variables, so that's why we need to use multivariate analysis to describe and deduce properties of the data. So machine learning enters here because it provides an automatic way to learn or fit an MBA statistical model using understood or training data to characterize data which is not understood. So that's why machine learning is referred as an artificial intelligence, because knowledge is extracted from experience that comes from the training data. So MBA and machine learning techniques have become very popular in many fields of science, but specifically in high energy physics, I list here the most important application of machine learning. For us, the most important one is the rejection of background against signal events when we want to do a measurement or analysis or a physics analysis. And luckily we have that the training data usually can be known by Monte Carlo simulation. So the classification is building a statistical model that is capable of distinguish between signal and background given a threshold. And the most popular classifiers that the people have been using recently are the boosted decision trees, artificial networks, and for this work we are gonna treat the support vector machines. To give a more clear idea of why the people are using more and more the MBA analysis, I make a comparison here between the more traditional cut-based analysis and the MBA analysis. So basically in these plots we can see how both of them are done. So in the cut-based analysis we do one-dimensional cuts, here one cut, and we try to discriminate between the signal and background, and here the same. Here we can see that the classification is better because the MBA method uses the correlation between the variables, while here only one-dimensional cuts that rely very heavily on human expertise are done. So the main advantage of using cut-based is that the systematics are very easily evaluated, whilst in the MBA method are more difficult to evaluate. But at the end, the people are preferring these methods because the statistical power is much better using MBA. So this is very helpful when there is a search of a very small signal in a detector. Okay, so we pick a definite support vector machine algorithm because it gives us a lot of nice properties. So at the end we want to do the same task, which is classifying between two different classes here, plus one and minus one, and the idea is to build a boundary. Here is just a line because we are dealing with linearly separable data that follows the optimization problem to maximize this distance, and this is done by building this equation subject to these conditions, right? But in real life we don't have this kind of problems. We have something which is not linearly separable. So to solve that problem, what support vector machine does is to do a mapping between the original feature space, which corresponds in this case to x1 and x2, to a mapped feature space where the data can be separated with a plane. You can imagine here the plane that separates very well the data. This is done again using a mapping and using something which is called the kernel trick, which enters here. And the most popular kernel that is being using, and is the one that we show in this presentation, is the Gaussian tree, the Gaussian kernel, and the parameters of this kernel and the support vector machine are C and sigma. Now that we have defined which machine learning algorithm we're gonna use, we wanted to improve its performance. So the way to improve it is using ensembles method. So basically an ensemble method is a combination of many classifiers to yield a classifier which is stronger. And the way to construct these ensembles is using boosting and bagging. Here we focus on boosting, which is combining a classifier using weights or boosting according to a specific rule. Here we focus to using the ADA boost because it's the one which is used by the high energy experiments, and basically here the rule to do the boosting is based on how the errors of the training classifiers, these are the training classifiers, behave with respect to the known classifiers. Here we build the weights, the errors, then we build the weights, and here we build a score. We repeat this procedure, and at the end we get a final classifier, which is a linear combination, which is weighted by these coefficients, which depends on the errors. So here we have a number of k classifiers. This final classifier is expected to be better because it is a voting procedure, so it takes the different features in a different way, so we have a stronger classifier. Now, why combine support vector machines and AdaBoost? Okay, the first reason is that both of them are simple to interpret, so this helps to assess the systematic uncertainties. Also, both, especially support vector machines, haven't been explored a lot with respect to other machine learning like VDTs or neural networks. And probably the most important one is that support vector machine doesn't need a lot of expertise to have a nice classifier. With, for example, if we compare with VDTs or neural networks, you have to be very careful of how to build your classifier. And also the support vector machine is quite accurate. And finally, the support vector machine is robust, allow statistics. And this is very important because in high energy physics, some more uncertainties are driven by statistical fluctuations. And this basically tells the precision of our measurement. Here outline on the right the strategy of how to improve the support vector machine, or how to do it. Here only 4 steps are presented today, and we study standard data that practitioners of machine learning use. Today I only show the Titanic dataset. The second step is to boost different hyperparameters, in this case the C and the sigma that we show in the previous slides. We also take care about the diversity to check how different each classifier is with respect to their others, and we get the test errors when we apply the trained classifier to test samples. Okay, let's jump to our results. So here in this plot I show what I call the hyperparameter grid search. So basically this is telling us how the support vector machine behaves with respect of the different sigma and C hyperparameters. So this actually is a very nice to see, because we were expecting that the most important parameter is the sigma, and this is exactly what we are seeing. So for example, here you can see that if we keep one sigma constant, we have the same test error, but if we vary the sigma, we have some changes. This line, this part actually corresponds to some overtraining, which is when the model fits very well to the statistical fluctuation of the training data. Here we have a plot that tells us the classification of each classifier in the ensemble. So this is telling us that the classification error is just above 50%, which is good. Okay, this is the most important result of this work. So that means that our study is actually giving us very nice results, because we can see that the test error is dropping very fast with respect of the number of classifiers. That means that in this point corresponds to only one classifier. We get more classifiers and the error gets smaller. So that means that the combination or the ensemble technique is working very well. Finally, I would like to talk about the diversity. So here we have the results of the diversity. So diversity is a test that we do to check how different the classifiers inside the ensemble are with respect to the others. So the more diverse the classifier is, the better. So that means that we want to build a classifier which is very diverse to have less errors. Here we have improved results with the cancer dataset. So we have that the AdaBoost without diversity applied, it's worse than with respect when we apply diversity, and also the number of classifiers changes, which is nice to see. This brings me to my last slide. So as a summary and outlook, I would like to say that the support vector machines, when boosted in ensemble, they work very well. So we implemented successfully this methodology. Early results are quite promising, and we would like to continue to exploring the strategies that I just listed in the previous slide to further improve this technique, and soon we will apply this to high energy physics data, and we hope to make a contribution to this field. Thank you very much for listening.